Okay, now for the exciting conclusion of section 3.1. Let me say that my son Ethan and I have put a lot of work into this, and we're learning a lot of stuff about making a little math tutorial like this. And it takes a lot of work, so we got to figure out ways to speed up the process here. So I'm going to use some videos that I found in my math lab and saves some of the work going on here. So what we want to do to wrap up this section is first look at example 2. This is the problem that we mentioned at the start of this section. This is page 171, by the way. And at the start, we had on my separate little board here the revenue model. That was the beginning discussion in the section. And the function that described revenues for this particular company selling this particular product. The revenue was R of x equals negative 0.1 times x squared plus 600x. And as we saw, of course, it's a quadratic function, therefore its graph is a parabola. And the parabola opens downwards, therefore the vertex represents a maximum value for R of x, which is our vertical axis there. So, if we wanted to answer the question, where do we get the greatest revenue? That means we're looking for the greatest y value, R of x in this case, and that implies the vertex of the graph. So, if I locate my vertex, I'll figure out how many TVs we have to sell. B is 600, so minus B is minus 600 over 2 times A. A is negative 0.1. If I just cancel out my minus signs, I can make life a little easier. And I get 600 over 0.2. If I get rid of my decimal sign, because I hate to rely on a calculator for something like this, I get 6,000 over 2, which equals 3,000. So, that tells me that the company needs to sell 3,000 TVs in order to maximize revenue. Alright, so that's an example of doing some modeling with a quadratic function. But let's look at the classic example of using a quadratic function. This was kind of the example for which calculus was invented, and studying parabolas was invented in order to get to calculus. You remember the story of Newton, Isaac Newton, sitting under the apple tree in England? And actually the reason he was out in the country is because they were having a pandemic in London, like we're having now. He was a wealthy gentleman. He just said, well, I'll just go to the country so I don't get sick. He went to the country. He was lying under the apple tree, leisurely hanging out. And the apple fell down and hit him. And he thought, why did that happen? Why did the apple fall? And he realized there's a force that's pulling things down. Everything goes down. There's something like gravity. And it began to dawn on him, something that's obvious to us now, but was obvious to nobody beforehand. There's this force going on. Things just don't fall of their own accord. Something's pulling the apple down to the ground. Well, after much research in physics and so forth, gravity was figured out very, very well. But for Newton, besides figuring out his 3 laws of physics, the laws of mechanics that he devised, he started working on calculus too. Now, all this math happened for him to figure that stuff out. But I'm going to demonstrate things to you here with my baseball. Remember I said I was a baseball fan. Watch the ball. What was that? It was a parabola. When you're watching a baseball game, a guy hits a high fly ball or a home run. You're watching a soccer player and she punts the ball, the goalie punts the ball. Every time you see that flying projectile, it's a parabola. Because the equation that models the parabola is this. And you might say, wow, what's that? Well, this is the height of the projectile. When something is kicked in the air, up into the air, or thrown into the air, t is the amount of time that elapses. V sub 0, as you'll learn in the video, is initial velocity. H sub 0 is initial height. Because as we see in this example 4, a ball is thrown off a building at the top of the building 80 feet high. The ball is thrown up at 64 feet per second. That's the velocity when it leaves the hand of the person throwing the ball. Of course, the ball is going to go in a parabolic course like that. And at some point it reaches a maximum and it comes back down. You're going to learn how to do that in the video that I will assign for homework. For now, let's look at some more algebra. It turns out that there's another very popular and useful form for a quadratic function. Vertex form. Vertex form looks like this, and this should be on about page 173 or so. If you write an expression like this where a and h and k are just constants, x is your variable, it turns out that is a quadratic function. If you were to, you see this is being squared, this binomial is being squared. If you were to multiply this out, you're going to get an x squared. And you're going to get that constant h squared. And in between, you're also going to get x terms with some number multiplying x. So in other words, it's going to match up to ax squared plus bx plus c. Now, the coefficient in here, I think I'll get this stuff out of the way. The coefficient in here, a, is the same. So if a is greater than 0, I say the same as the form that we're used to looking at. If a is greater than 0, the parabola opens upward. If a is less than 0, it opens downward. And the most useful thing is this. The point h comma k is the vertex. Notice, be forewarned, h is being subtracted from x. K is being added on at the end. So one of the numbers is getting subtracted, one is getting added. Don't get them mixed up. And of course, since the x-coordinate of your vertex is the number h, then x equals h is your axis of symmetry. Let's squeeze in right here this example. It's figure 3.13 on page 174 in your textbook. Here is a quadratic function written in vertex form. We look at this and we see that the vertex has x coordinate 2, right? 2 plays the role of h. 3 plays the role of k. So that's the y coordinate of my vertex. A equals 2, so the parabola opens upward. And the y-intercept, well, I have to do algebra to figure that out. I take my equation here, replace x with 0, right, to find the y-intercept, and calculate the result. And it turns out to be 11. So there in figure 3.13, you can locate all those points, the y-intercept, the vertex. I wouldn't bother with x-intercepts at this point. In fact, this particular parabola does not hit the x-axis, if you notice. And you see what it looks like. It's a parabola that opens upwards. Okay, at this point, do number 22 on page 177, and we'll be right back. Okay, so you should have just completed problem number 22. Let me put the solution up here quickly. This is 22. I see that the vertex is negative 10. Because remember, you have to be subtracting the number from x. So when we have x plus 10, that means x minus a negative 10. And we have to add k. So we're adding a negative 6, which tells me k is negative 6. Therefore, my vertex occurs there at negative 10, negative 6. Y-intercept. Well, I just put x into this. By the way, I forgot my exponent again. I just did that earlier today. Let's get my exponent back in there. So I replace x with 0, and this number here evaluates to 94. A is the invisible 1, it's a positive number, so the parabola opens upwards, and our graph would look like this. Vertex is down here at negative 10, if I am marking all these these gradations down here as units of 5. And y-intercept is way up here above 90. So I have a tall, skinny parabola that opens upwards like that. Okay, and even though we haven't located x-intercepts, we still have a pretty accurate drawing. So that's certainly a good graph of that parabola. All right, let's get on to our modeling example, and that will wrap up our section. Example 5. This is on page 1 75. Let me find it in my textbook. Minimizing cost. The cost for producing X Champions golf hats is given by the function C of X equals 0.2 times X minus 40 squared plus $200. Okay, of course, we're going to write down our function here. 0.2 times the quantity X minus 40 squared plus 200. A, find the vertex of this function. Well, we can look right here and see that the vertex is 40. We're subtracting that number and we're adding this number. Perfect. That tells me K is 200. So there's my vertex. Part B, is it opening upward or downward? Well, A is 0.2, that's a positive number, therefore it opens upward, and therefore, since the parabola opens upward like this, we are talking about a minimum occurring at the vertex. In part C, it asks you to draw a quick graph. Well, if you were to plug 0 in here and multiply all this out, you would get 520 as your y-intercept. We see that at 40, this is 20, this is 40, this is 60, so on and so forth. At 40, we have our minimum. And the y value at that minimum is 200. So if this is 500 here, then the x-intercept is 520, just above it. Then way down here is where my vertex is. So I have a parabola, pretty flat, that looks like this. I'll label this vertical axis C of X because that's the variable given to us in the formula. Then the last question says, for x between 0 and 40, what's going on? Well, from 0 at the origin there out to here, the parabola is going downwards. It's decreasing. So that means cost is decreasing over that period there, over that interval. So up to making, what is it, hats, 40 hats? Cost is decreasing per hat, but after that, when we start making more hats, cost is increasing. So that's what that tells us. All right, let me put your homework up here. I think in the future I'll probably be putting it out in an announcement, but for now we'll just do it the old-fashioned way. Homework. It all starts on page 177. 1, 3, 15, then 21 through 29 odd, and then 49 and 53. So there's a lot of homework. This was the big section, a lot of material. And then go to My Math Lab, right? Go to your Math Lab page, and you know, that's where you're looking at your e-book, your virtual book. But go into your homework assignments and you will see a homework assignment that tells you to watch a video. And I've named the homework assignment 3.1 video. Thanks, and I hope to be hearing from you soon via email, and we'll work on problems together. See you soon.